So last session we covered deep lab and we started covering context aggregation because context matters when you want to do semantic segmentation. And this paper is nice because it's going to give us a new perspective on convolutions as well. And it should be able to help us put the pieces of the puzzle together because we know about convolutions and convolutions have been around, I don't know, things forever. So they are not something new, but how are they related to the convolutions that we see in computer vision? This paper is going to give us the mathematical formula. So you can think of your images as functions, you can think of your kernels as functions, and you can convolve them, and you can introduce dilated convolutions. And for this paper, it's very important for them to make a distinction among the terminology. Some people use atruse convolutions, some people use dilated convolutions, some people use convolutions with holes, etc. That's okay. You're going to see that in different papers. But if you want to be precise, dilated convolutions is the correct name because originally it was atruse. It was an algorithm. It's the name of an algorithm. And it was for wavelet decomposition. And they were using dilated convolutions. So probably a better terminology is dilated convolutions rather than atruse convolutions, but it's not a big deal. It's just terminology. Potato, potato, it doesn't matter that much. But the cool thing is that you can use dilated convolutions to support exponentially expanding receptive fields, which is nice. And the way you do it, you're gonna start working with powers of 2 as your dilation factor or dilation rate. And you're gonna keep convolving with 3x3 filters. And this is gonna enable you to have a very large receptive field. And this is a precise definition of what a receptive field is. Any pixel in your original image that's affecting the current pixel in your current layer through some computations, that's going to be part of your receptive field. And when you do powers of 2, you're going to end up with the size of your receptive field exponentially growing. The deeper you go, the size of the receptive field is going to grow exponentially. And last session, we started discussing this, and we had some discussions over what this figure means. I think it's better to think about it this way. These red points are the points that are directly affecting the current pixel in your current layer. And these 9 points are the ones that are affecting the center point in your next layer. And the dilation factor originally is 0. It's 2 to the power 0. That's going to be a 1. So that's just a 3x3 convolution. And that's going to be your receptive field. Now you have a convolution with a dilation factor of 2 for the next layer. And this is a dilation. So these 9 points, the red ones, are going to affect a single point in the next layer. And each one of these points have a receptive field of 3x3 because of what we just discovered from the previous layer. So these ones are going to have receptive fields of 3x3, and the final receptive field is going to be this in the original image. Now let's go to dilation factor of 4. It's 2 to the power 2. So these points are going to be 4 pixels apart. And these 9 red pixels in this layer are going to affect 1 pixel in the next layer. And each one of them have a receptive field of this big. And that's coming from panel B of this figure. So each one have a receptive field of that size. And if you put everything together, the final receptive field of these operations is going to be bigger, and it's growing exponentially. And then we moved on to context network architecture. So what network architecture are they using? The first 2 layers are going to have a dilation factor of 1, and then the dilation is going to be powers of 2. And you're going to have 2 architectures in terms of your channel size. One is the basic, where the channel sizes are the same, and the other one has channel sizes being different. But then it's a matter of training this network. And when they trained it, when they sat behind the computer and they trained it, the network didn't converge. And it had to do with the way that you have to initialize your network. So initialization matters. You can use identity initializations for your filters, and apparently that solved the problem. because now you're taking your image, and initially during the initial phase of your training, you're just pushing your image to the end. It's just the identity map. And we know that identity helps. We saw that in residual networks paper, in ResNets. So it's trying to be, at least initially, similar to a residual network, and then later on depart from it based on the training, how the training goes. This is for the basic architecture. If your architecture is having different channels from one layer to the next one, like from here to here and from here to the next one, then we cannot use this identity mapping anymore. It's going to be a little bit more complex to initialize and to come up with identity initializations, or as close as possible to identity. And this is just a generalization of the formula you see up there. And to see that, CI and CI plus 1 are the number of channels, number of filter maps in 2 consecutive layers. So for instance, it's going to be 8C and 16C. And let's assume they're the same. Let's say we are with the basic network for now. And C is a number that's dividing both of them. So that's going to be the common divisor. And let's say C, CI, and CI plus 1 are the same. So when you do the division, you're going to get a 1 here. C divided by that is going to give you A, because these are the same, and that's going to give you B. So that's going to give you the identity initialization. So yes, it's a general formula compared to that one. And there is a question for those A and B indices. We are assuming a flattened feature map? Not really. So you have 2 components to your kernel. One is taking care of your pixels, T, and if you remember, T is a number, is a pair of numbers. From negative R to R, it's a pair of integers. So that's going to be your index. And what we are saying is that on the diagonal of our image, of our kernel, we are setting a 1, then we are setting a bunch of zeros off diagonal. And channel-wise, these are going to be matrices, your kernels, that are taking you from one dimension to the next one, from dimension C to the next one. On the diagonal of that matrix, you have also the identity, 1, otherwise it's 0. Yes, so the question is A, B, T are each tuples. T is a pair of numbers, pair of integers from negative R to R. A is a scalar, B is a scalar. These are your matrix entries. T is a tuple, A and B are scalars, are integers. Does that answer your question?
It says here, though, that A is the index of the input feature map.
Say it again.
Right here in the where your cursor is below, it says A is the index of the input feature map, and B is the index.
Exactly. So these are scalars, and T is a pixel.
Okay.
T is 2-dimensional, A is 1-dimensional.
Because we have like multiple input feature maps and multiple output feature maps, I think is.
Exactly, yes.
And a feature map is like an array, basically, or a matrix.
Exactly. So each feature map is a tensor. It has a bunch of pixels and it has a number of channels. But in the end, you're gonna get an identity out of this kernel. And initially, that's your initialization, and you let it train. What is the backbone, or what is the front end of your network? That's gonna be VGG16. And your input are padded images, and you're using reflection padding like UNet was using. And in the end, you're gonna get a low resolution tensor with 21 channels, because you have 21 classes in Pascal VOC. And then you have to increase the resolution, go back to the original resolution, and then you do your prediction. So there is an upsampling going on after this layer. And let's compare this to fully convolutional networks. And with DeepLab, the previous late paper that we covered, and DeepLab multi-scale images. And with this front end and dilated convolutions constructed this way, you're getting more context. And because you have more context of the entire image, you have a bigger field of view. You can increase the intersection over unit. That's your metric. And qualitatively, these are the type of predictions that you're gonna get. This is your front end. If you add the context using dilated convolutions, you are able to get rid of some of these confusions that your network is making. And when you add CRF, you're gonna get better results. And we know what CRF is. We covered it last session. It's just a post-processing step, and we can compare it with the ground truth. So these are really good predictions.
Does that CRF, was the CRF we talked about, did that also include some RNN, or is this different, this CRF?
No, that one didn't include any RNNs, but you can include it. But whatever you do, that's a post-processing step. And in terms of numbers, front end, your basic network, the large one, is doing the best in terms of mean intersection over union. If you add CRF, you're gonna add a little bit of improvement. CRF you can apply to any the predictions of any network. So it's gonna improve the prediction. And any other questions before I move on to the next? Okay, perfect.